Hey, welcome back to Fat Mama Physics. In this video, we're going to do example 2 from 5.1b, electric field and electric potential energy. This one is on, let's see. Okay, where the electric field is 0. So, let's get started. Well then, two positive point charges, Q1 and Q2, so why not we label this? Q1 here is 16 microcoulombs, and Q2 is 4 microcoulombs. Separated in a vacuum by a distance of 3 meters as labeled here in the diagram. Find the, where it is. Find the spot on the line between the two charges where the net electric field is 0. So look, this question shows us right there where P is, and it's actually showing the two vectors where E2 and E1 are going to be exactly the same. And you're wondering, wait, why is this E2? It's pointing towards Q1. But don't forget, when you draw the electric field from a positive charge, the electric field points away from the positive charge. Okay, so just don't want to interfere with any of the diagrams here. Okay, so essentially what's going to happen with with Q1, the electric field from Q1, which I'll highlight with purple, is going to point towards, Q, away from Q1. So it's going to point in this direction. And Q2, since the electric field points away from the positive charge, this guy is going to point away from Q2, so at point P, the electric field line due to Q2 will be towards Q1. So some point in the middle, the electric field is going to be exactly the same. And notice that it's a little bit closer to the 4 microcoulomb as opposed to 16 one, since both charges, the electric field due to both is directly proportional to the inverse of the distance. A smaller charge means that the field is not going to be as strong at P, so it needs a little further distance from the stronger charge, a little bit closer to the weaker charge, for the two fields to be the same. If we wanted to, we can draw a little tiny diagram here how the field lines could look like. So for this positive charge, here, the field kind of points away like this. For this one, it kind of looks like that. Oops. Okay, so if I want to continue drawing this. And for the stronger charge, of course, the electric field lines are going to be more densely packed together versus the weaker charge. Okay, so notice that there's that line here in between. That's where the electric field would be 0, regardless if you're putting an electron or a proton, or positive or negative charge. Their electric field is going to be 0, so there's a nice little sweet spot. But if you tip it over and tip the balance of it, then it's going to start to move, okay? All right, cool. Let's draw the, now we know the conditions. Now we can go ahead and write our equation. So, from a magnitude's perspective, the electric field due to charge 2 is going to be exactly the same as the electric field due to charge 1 at that point. Wait a second, there has to be a point here. So we do know a few things. We know that the total distance between the two charges is 3 meters. We don't know where P is, but let's set that distance as D from Q1. Okay, so notice it's labeled there in the question, and which means that the remaining distance from P to Q2 is going to be 3 meters minus D. Okay, so it's the whole thing minus D is going to give us the remaining portion. So when we put this into our equation, for E2, that's Q2, the electric field is going to be KQ2 over whatever that distance is going to be 3 meters minus D squared, okay? Yeah, so don't forget the electric field is KQ over R squared, and that's going to be equal to KQ1 over D, which is just this D over here, squared. Don't forget the square. Okay, so I am not gonna, again, I'm not gonna put in positive or negatives, and since they're both positive charges, it really doesn't matter. But since I've considered the directionality already, I don't need to worry about putting in negatives and positives, even if we're dealing with a negative charge. Ooh, a negative charge. Then, same idea. But negative charge, they will cancel anyways. Speaking of canceling, these k values will cancel, so let's get rid of them first. I'm going to multiply this d2 up over here. I'm going to multiply both sides by d2, d2, so I get q2, d2, and I'm going to multiply this ugly thing up on top as well. 3m minus d, or 3 meters actually, so I'll get rid of the m so it doesn't confuse us. It's not another variable, it's just me writing 3 meters squared. Okay, so after I multiply that, that gets rid of that up on top. Hopefully our algebra skills are functioning right now. So if I rewrite this, I get q2 times d squared is equal to q1 times 3, there should be minus d squared. The numbers look very ugly right now. So we could do some algebra here. We could do solve a quadratic. But I just noticed something interesting about the numbers. So I'm just going to plug in the numbers first. Q2 is 4 microcoulombs. And I'm actually just going to work with 4. And whatever answer that I simplify this to, I know I have to... well, you know what? Guess what? Take a look at this. Because this is 4 microcoulombs, right? Times d squared. And Q1 is 16 microcoulombs times 3 minus d. All of that to the power 2. And the interesting thing here is, it's not something big. But since the same units appear on both sides of the equation, on both terms, only those two terms, and only those two terms exist, I can just get rid of those 2 units. Okay, and the other interesting thing is, guess what? 4 can be expressed as a power of 2 as well. So guess what? You know what? I'm going to square root both sides of this equation because it's going to look very nice. All the numbers work out very well. Okay, and after I do that, the square root of 4 is going to be 2. The square root of d squared is going to be d, okay? The square root of 16 is going to be 16. The square root of this bracket, 3 minus d, is going to be 3 minus d. And look at that. It looks so much better. So let's just distribute everything out. I get... oh, sorry, that's 4, by the way. So the square root of 16 is 4. What am I doing? Okay? So then after I distribute everything out, I get 12... minus 4d. Hey, looks beautiful. And if I just do a little bit of algebra here, add the 4d to both sides of the equation, then I'm going to get 6d is equal to 12. And ultimately, this is going to give me 12 divided by 6. And so d is just going to be equal to 2. And since the original measurement was in meters, since this 3 was here measured in meters, then this must give me 2 meters as well. So d is 2 meters, and using significant figures, this is going to be 2.0 meters from Q1. And that's assuming that the d is somewhere in between Q1 and Q2. Okay? Alright, so that was example 2. And guess what? These are interesting questions because especially if you have, say, a positive and a negative charge, or negative and negative charge, then the after you draw the electric field lines, there's only certain charges or combination of charges where you're going to get a nice sweet spot in between. For example, a positive and negative charge, the electric field lines go from the positive charge all the way to the negative charge, meaning there is not going to be any spot between the two charges where the electric field is 0. So with a positive you can get that. Negative you can get that, but not with a positive negative. So that's interesting stuff that you can expect in certain questions. But this is what we got. Here's example 2. Thanks for watching. Stay tuned for example 3. Fat Mama Physics signing out.